Okay, so there were some very good questions in the break. You feel free to ask these questions during the lecture because I think everyone profits from questions like this. Or you also feel free to come in the breaks and ask questions. So this is just an example. We'll skip over this. Okay, so this is one thing I want to show you. What is the effect of curvature and strain? You see, these are two different experiments. This here is an experiment in the spherical chamber I mentioned earlier. So you see here, this is now SB, the burning velocity with respect to the burned. And then this is equal to the RDT because VB is 0. So the kinematic relation here, the kinematic relation in the burned, because UB here is 0, it just says the XDT is equal to SLB. So this here is just the observed quantity. Now, you see this flame is spherical, it propagates, and the larger the flame becomes, the smaller the curvature becomes, okay, or the flame curvature. And so you start here, so this curvature, and then you start here, and you move to larger and larger, or this flame stretch, but you could say this is basically, it signifies the curvature. So if you move to larger flames, then you see this term here, the curvature becomes smaller, this term becomes smaller, and you approach this SB 0 in this case. You see it's almost linear. The measurement here is always linear. This here, by the way, is interesting. We didn't question that yet. But it just says that SL is linear in curvature, and it's linear in strain. And you see here this linear assumption, not so bad. This here is a different experiment. This here is a counterflow burner where you have a premixed stream from the top and a premixed stream from the bottom. And then, you have two flames. This is is from a paper we published with Professor Egofopoulos from USC. He runs this counterflow burner, and then you can change the velocities, and with that you change the strain. We'll look at this later on. And then here, if you go to smaller and smaller strain, then you see the burning velocity gets smaller and smaller. And also here, this linear relationship here is quite good, except here for very small values of strain. The linear relationship is not so accurate anymore. So what you do here, when you want to measure the burning velocity, you see this is a measurement here, and this still depends on strain. So you measure this as function of strain, and then you extrapolate to 0 strain. That's how these experiments are done, and the same here for this, for the 0 curvature, and same here for the strain. Okay, so then let's talk about these instabilities here real quick. There is the two main instabilities here, the thermodiffusive instability and the hydrodynamic instability. The thermodiffusive instability, basically I explained it already earlier. Let's say you have a flame here like this, then this here, so this is unburned and this is burned. Then this here would be a positive curvature, and this here is a negative curvature. And you see if the Markstein length here is positive, then for positive curvature, this is negative, so it makes the burning velocity slower. So you see you take this bump out, and here it will be faster, and so you make this faster. So you take out these flame corrugations. It has a stabilizing effect. However, if the Markstein length here is less than 0, is negative, and that is the case, for example, for lean hydrogen flames, then you see this is positive curvature. The Markstein number is negative, and the Markstein length is negative, and so this will be faster. So this has a destabilizing effect. The parts of the flame that are ahead, of the mean, they will become faster, and this will become slower and slower, and so this leads to an instability. And that's why, lean hydrogen flames are very different from other hydrocarbon flames. Okay, so why is this? Why? How, how does this physically happen? You can imagine you have in this region here you have hydrogen. Now the hydrogen. So you have, and here you have hot temperature. The hot temperature preheats the unburned gases, but now the hydrogen, it diffuses very, very quickly to the region where the right temperature is reached. So locally, you can imagine, is a little richer at the place that has the right temperature. And if it's a little richer, then the flame burns faster. And the same here, because this is richer now, this has to be leaner on average. And so this is why this here stays behind. And it can become so lean here that actually the burning stops completely. And then, there's no flame anymore. There's just, something interesting, let's say. Okay, so that's just in a few words, the thermodiffusive instability. The thermodiffusive instability is very hard to analyze. Hydrodynamic instability is also not so easy to analyze, but there has been a lot of work on this hydrodynamic instability. The hydrodynamic instability has one very, very interesting feature, which maybe comes unexpected to those who don't know this yet. So it's interesting. So this is how this works. The hydrodynamic instability, here has nothing to do with flame structure, Lewis number, or whatever. It's just the hydrodynamics of the flame. For the purpose of looking at this, we can again assume the flame is infinitely thin. And then you start out here with a slightly corrugated flame, let's say. And then what happens is that if the flame is slightly corrugated, then because of the gas expansion, the flow is accelerated behind the flame, and the streamlines here, they are deflected again. Okay, so you see that if you start here, let's say with a stream tube, a certain volume here of flow that comes towards the flame, because the streamlines are deflected. You see they go towards each other around this little corrugation of the flame, towards each other, so you build up a pressure at that point. This pressure also will modify the flow ahead of the flame, so the streamlines diverge ahead of the flame. Okay? So, now think about, you have a flow coming in here. The mass flow is rho times U times A. And now, let's say the density doesn't change, but this A, the area of the stream tube gets larger, and this means the velocity has to get slower. Okay? So this is interesting. This flame moves in this direction. It moves here to the left. And whenever you have a corrugation into the unburned, then that part of the flame, the burning velocity stays the same, but the velocity ahead of the flame gets slower, so that moves faster into this region. Okay? So because this is slower now, this will move a little faster into this region. Because this here is faster now, you see here you have the opposite effect. This flame will move more slowly into this region, and you get an instability. It's not stable. Okay? Interesting is we have not made any assumption about Lewis number or whatever. The only assumption we made here was that the heat release causes a density change, acceleration of the flow, which is not an assumption. We know that's the case. Okay, so interesting then is that you form an instability, and that instability, that flame, is unconditionally unstable. Okay? It's always unstable. What this means is that all flames should be unstable at all times. Isn't that interesting? Does that match your expectation, your experience? No, sometimes you see flames burning very stably. So why is that then? I didn't make an assumption here. I just said you have a heat release, and that's it.
In what sense do you mean unstable? Specifically only the heat release?
unstable here means that if you have a little perturbation in the flame, it will grow and grow and grow. That's it. Okay, that's an instability. You shouldn't see a Bunsen flame. This should go wild immediately due to the instability. Actually, you see that in maybe we come to that later on. High pressure flames, they develop these cellular structures and so on. Yeah, you wanted to say something? No. Right. So we mentioned earlier there's also these Lewis number effects, diffusive effects, and so on. And they have not been, we haven't talked about these. Okay? So, but you can do this does not exclude all diffusive processes, because the burning velocity, we just assumed this moves with a flame speed or with a burning velocity, and that burning velocity, of course, is a manifestation of the interaction of transport and chemistry. So it includes the transport. But so you can do an analysis here. You can do a stability analysis, with a few assumptions, whatever. And this stability analysis is shown here after this, but here we just want to look at the result. It's just a stability analysis, like you do a linearization, you get an eigenvalue, you do a perturbation, you get an eigenvalue problem, and so on. So it's a standard analysis, and this is what it is. So this here is the so-called dispersion relation, which gives you the growth rate as function of the wave number of the perturbation. Okay? And what you see here is that red line here. That is the case we just discussed. And that just says for any wave number, so dispersion relation, you know these things. The way this works is this is the growth rate of a perturbation. If it's positive, you get an instability. It's negative, it has a stabilizing effect. Okay? So you see that for all wave numbers, so the wave number is 1 over the wavelength, which means large wave number is a small wavelength perturbation. And you see for all wave numbers, this growth rate is positive, which means it's always unstable, unconditionally unstable. Okay? But now this is a little more complicated now. You can do the stability analysis including these Markstein effects, the stretch effects. And then you see if the Markstein number is positive, negative Markstein number is for these, at least for these, negative Markstein number gives you an instability anyways, okay? But positive Markstein number now has a stabilizing effect, at least to these curves, where you see this here, for a certain value here of the Markstein number, this is still unstable up to this point, but for higher values here, higher wave number values, it is stable. And the larger the Markstein length is, the more, or the smaller the unstable region here becomes. So basically, the reason why you don't see instabilities all the time is in flames, this hydrodynamic instability, is the stabilizing effect of the these Markstein, these stretch effects. Okay, the question. Pardon?
Is this diagram for a specific case or is it general diagram?
What does so the question is, does it?
Is it for a specific fuel or case, or is it a?
Yeah, no. This is so. The question is, is this for a special fuel or a special case, or is it general? This is a general, but again, it's a simple analysis that just starts out just with a propagation. So all the fuel effects, they would be in the SL and in the Markstein length. Okay, could be any fuel, and you just specify these values according to that fuel. Yes.
So as we are increasing the Markstein length, we see that these perturbations are no longer there, or like diminishing the instability. So what's physically happening?
Yes, so what's physically happened, so the question is, when the Mach-Stein length gets larger, then you get, it gets more stable, and why is that? And what you have is just the larger the Mach-Stein length is, the stronger this curvature stretch effect. And what we saw here was that if the Mach-Stein number is large, then this has a very strong influence. And if you start with an original perturbation here like this, then you see the positive curvature will get slower, this will get faster, and has a stabilizing effect. The larger the Mach-Stein length is, the stronger this stabilizing effect. So you have the hydrodynamic instability, which always wants to cause an instability, and then you have the Mach-Stein number effect, which for positive Mach-Stein number tries to decrease the instability. For negative Mach-Stein number, it would just add to the instability. Okay? Okay, so this after this you will just see the analysis here. So if you're interested in going through this, then enjoy. A little exercise here, and then let's see. Oh, that's the end of this lecture. So in this lecture here, we talked about kinematics of the flame. We introduced the concept of a burning velocity. We derived, so once you have the burning velocity, then we said now, if you assume that the flame is just thin and it's just a front moving towards the fuel air mixture, then we can derive an equation that describes the evolution of this. And this was this G equation, or the level set equation. The level set equation itself doesn't have a chemical source term. All the effects of chemistry and the interaction of the chemistry with diffusion and the flow field, they're all captured in the burning velocity. And the burning velocity is itself, you saw, is the unstretched burning velocity, which is just a parameter of the fuel that you can measure or compute, plus these stretch effects, which are curvature and strain. And so we talked about these. We looked at, without any derivation, we looked at these results from the asymptotic analysis by Clavin and Williams and Matalon and Markowski. And then we talked about how instabilities can occur at the end due to hydrodynamic effects and due to these diffusive Lewis number effects. Okay, any questions about this? Okay, so then we want to go to the, you could say the more interesting part, or maybe not, I don't know, but the flame structure. Now we said the flame is infinitely thin, and there's a burning velocity, and now we want to look at, we want to zoom into the flame, into this, what we call infinitely thin. We want to zoom into the structure, look at how the flame looks inside, and then see why is the burning velocity what it is? Why does it have this value and not a different value? Okay, so that's what we'll do here. We look more at the details, and we'll find relations also for the burning velocity. We do this in two different steps. We'll start out with a very classical analysis, which is the so-called thermal flame theory. Thermal flame theory because it's based on a one-step global reaction. One-step global reaction, again, it doesn't have any radicals, it doesn't have any intermediate products like CO. It just has fuel goes to products. And the only dynamics that are captured by this are thermal effects. The reaction rate is given as some exponential function of temperature. And so reaction rates become fast when the temperature is high, and they become very, very slow when the temperature is low. Okay, that's why it's called the thermal flame theory. And so we'll talk about this, and there are some things that are quite interesting about this. Also, what's interesting, it's relatively simple. It's an analysis that we can go through here in just a few minutes. At the same time, it's an asymptotic analysis. So you see there are assumptions that are being made, which, you know, looking back, this was done many, many years back, looks like ingenious assumptions to make. And now we know, you know, from doing detailed calculations, we know these assumptions are right. But I think it's interesting. Also to see how this analysis is done. I mean, maybe we go through this even more to show you how to do these analyses in general in a simple example rather than to look exactly at this particular one. Okay, so that's the thermal flame theory. We'll talk about flame thickness, flame time that results from this. And then we'll see the one-step global reaction is not right. In real life, you have multi-step kinetics, you have radicals and all these things, and we'll talk about a reduced mechanism, the so-called four-step mechanism for methane air flames. We'll talk about the three-step mechanism. We'll talk about the two-step mechanism, and all of these steps, there's a certain reason why we look at these. And then there's an asymptotic analysis based on these multi-step chemical kinetics also, and we'll talk about this. And then at the end, we'll talk about analytic expressions for burning velocities, and then very briefly here about flammability limits, which all a result of this analysis. So the basic core here is three things: thermal flame theory, the four-step mechanism, and the asymptotic structure here of these flames. The rest is all on the side. Okay. Thermal flame theory here was done by Zeldovich and Frank Kamenetsky, 1938. Is a classic example of a nice mathematical description, and also was the foundation here really for combustion, for forming a mathematical basis for combustion science. You know, of course, that people have used asymptotics even earlier in fluid mechanics. The boundary layer theory, for example, is an asymptotic theory, and so on. But chemistry is complicated, and you'll see. I mean, it is quite complicated. And really, what you want is you want to get, at the end of the day, you want to have analytic expressions. Because if you have a differential equation or whatever, it's very hard to understand sometimes. If you have an analytic expression, you make enough assumptions, you get an analytic expression. It might not be very accurate anymore, I mean, quantitatively. But maybe it shows you really how different things are connected, and it really helps you to understand the physics or the basic foundation of the nonlinear interaction of all the different processes. So that's what we do here. Starting point: stationary flat flame front, like this. We talked about this earlier, how this structure looks like. The assumption here is that you divide the flame into three different zones. One is here the so-called preheat region. The preheat region is chemically inert, and it just raises the temperature of the reactants to this so-called ignition temperature. And then you have the reaction zone, which is the region between the ignition temperature and equilibrium, which is where all the chemistry takes place. And then behind the flame, then there's an equilibrium region where nothing happens anymore. Okay, so that's the idea. Here we talked about these things here earlier. You have heat conduction here. Species diffuse into the flame front, and so on. And we also introduced this ignition temperature vaguely earlier. Okay, simplification here. We want to use a one-step global reaction. Fuel plus oxygen goes to products. And then the reaction rate, it looks like this. B is the pre-exponential factor. That is just a basically it carries the time scale, and then here this concentration of fuel times concentration of oxygen times this exponential function. Okay, and you see this is complicated. It's nonlinear. It's nonlinear in many different, in at least 3 different ways. The first nonlinearity is you have there's 1 over temperature. 1 over temperature, 1 divided by temperature. That's a nonlinear function. Okay, that's the first nonlinearity. The second one is you have the exponential function of this. Exponential function, of course, is that's a very nonlinear function. So that's the second nonlinearity. And then you see the temperature is part of the solution, but oxygen also and fuel also. And you see you multiply these into each other, and that again creates a nonlinearity. Okay, because the fuel mass fraction depends on temperature, and the temperature depends on the fuel mass fraction. Okay, so these are and we'll see this later on a little more clearly, but this is a very nonlinear function. So the assumptions here. Ahead of the flame or behind of the flame front here, reaction rate is 0. Fuel or oxygen or both reactants are completely consumed, like you would expect. And in the equilibrium zone, either fuel is 0 or oxygen is 0. So the product of these two is equal to 0. Then a few more assumptions here, but they're not so important. But interesting here again is we can use coupling functions now. Is one-step global reaction, which means if I convert 1 mole of fuel to products, I have a certain thermal energy release. So the temperature and the mass fractions, they're coupled. And as a matter of fact, this is a coupling function. You see a coupling function between fuel and temperature, and this is between oxygen and temperature. And these relations we derived yesterday, if you look back at your, I should have pointed it out at that point, but if you look back at where we computed the adiabatic flame temperature, we derived these relations here. So this is good. Again, I told you how important coupling functions are. This is very important because you see here I have 3 unknowns: Y fuel, Y oxygen, temperature. I can replace, in this reaction rate, I can replace YF by the temperature, and I can replace YO2 by the temperature. Okay? So basically, if I plug this in here, I have something here like B times something temperature times exponential minus 1 over temperature. So there's only 1 unknown. So I have 1 equation I need to solve, and the whole problem is solved. So we make a low Mach number assumption here. Pressure is constant. So everything is now just a function of temperature. Again, we can integrate continuity equation here. Rho V is equal to rho U times SL. And then this is the temperature equation. And so this is the only equation we need. You see it has SL, is what we want at the end of the day. It has the chemical source term, and the chemical source term now is quite complex. It's very nonlinear, okay? So it's not easy to integrate this. So this is where we need to start making assumptions here. First assumption, preheat zone. The preheat zone is where the temperature is smaller than the ignition temperature. Ignition temperature is where we say this is where things should start. So we want to say at lower temperatures, omega is 0. Does that make sense? Well, it's not exactly true, but it's a good assumption because you have this exponential dependence, and the exponential dependence, it basically says that you go to lower temperature, the reaction rate gets exponentially small. Okay? This exponential function now, this is not enough. This is not enough at this point. Okay? Because the exponential function, there's a coefficient in the exponential function. And if this coefficient here, look here, there's this E, the activation energy. If E is 0, then what I just said is not true anymore. Okay? If E goes to infinity, then you change the temperature by just a little bit, and you get a huge change in the reaction rate. Okay? So all we do here, everything we do here, is in the limit of large activation energy. So that's what's called large activation energy asymptotics, which means that if the temperature goes down a little bit, then the reaction rate gets very, very small. Okay? So that's why we can say, because we are looking at the large activation energy limit, that's why we can say, if the temperature is lower than whatever temperature, something we define, there are no reactions. And then we say for a temperature larger than this temperature, the convection term should be very small compared to the diffusion term and the reaction term. And that's something that's hard to understand, but I don't know how they figured it out at that time. But it's true. This is a really good assumption. If you look at the balance in this equation here, in the reaction zone where things take place, then you will see this term here balances this term, and the convection term is basically unimportant. It's very, very small. Okay? Now, here we don't argue very much, but you can compare these terms here also using asymptotic theory or singular asymptotic expansion. You can also argue the reaction zone itself is a very thin layer, is like a boundary layer, and therefore the diffusive term must be very, very large, and because of this should be small. So there are different arguments you can make. So now, if we now do the analysis, we look at the first assumption. So now we have two different zones that we want to analyze. One's the preheat zone, one is the reaction zone. Preheat zone, this is the equation. We said there's no reaction, so this is the equation. Convection is equal to the diffusion term. That's not so bad because this here is a constant. Okay, so you see I can integrate this. Okay, so just integrate here left and right side, and you see dt dx is then equal to T minus T unburned, and then you get lambda over Cp rho as L here is a factor. Okay? So that's what I get for the preheat zone. That's interesting because, written again here, so at x equal to xi, so where at Ti, this is the condition for the gradient. Now, this is interesting. You see immediately that this is a exponential increase, right? Because you can integrate this here. You can say dt divided by t is equal to dx, and integrate this, you get ln, put it on the other side, this is an exponential increase. So you get exponential temperature increase in the preheat region, okay? So now, second assumption, now we want to look at the reaction zone. Reaction zone, we say the convection term is 0. So diffusion is equal to chemical source term. Because the temperature is a function of x, or the unique function of x, we can replace the d by dx here. The d by dx, we can replace it by dt by dx, d by dt. Okay? And then you see you can move the dt dx inside. And then you have a d by dt here. So this is the diffusion term, and this is the reaction term. And you see now I can integrate this in temperature. Okay? So integrate the left side in temperature, you just get this gradient again. Integrate the right-hand side in temperature, this is very nonlinear, that's even more complicated. Okay? But you can do that, so left-hand side here again, you integrate this in temperature, you get the temperature gradient. So I integrate this from minus infinity, from xi to infinity. At infinity, the gradient is 0, so I just get dt dx here is equal to now the integral, temperature integral of the reaction source term, okay, or the square root of this. Okay, this is what it is. Okay, so now I have a solution for the temperature gradient in the preheat region and one in the reaction zone, right? Or let's say let me go back. This is a crucial point now. I have the temperature gradient computed in the preheat, from the preheat region, from the analysis of the preheat region at this point, and I have the temperature gradient computed from the burnt region at this point. Okay? They have to be the same, right? At the same time, you have, this here, so these are now, they're first order equations. So I can specify one boundary condition. This here needs to satisfy the boundary condition at minus infinity. This one here needs to satisfy the boundary condition at plus infinity. The gradient needs to go to 0 at plus infinity. And then I also have this condition, okay? This kind of overdetermines the system. So this, always when you have an overdetermined system, it leads to an eigenvalue problem. There must be one parameter in the system that you have to adjust such that this condition is true, okay? So that's, so these two have to be the same, and that gives you a condition, so that is an overdetermination, or it leads to some parameter, you know, that has to have a special value so that this is true, and that is the burning velocity. So this is now so it's called the matching of the preheat zone solution and the reaction zone solution. The matching of this gives you a condition for the burning velocity. Okay, so that's it. You can just you see, I have an analytic form here for W for the reaction rate. So I can numerically, let's say, integrate this, and then here I can just compute SL from this. Okay, so basically we're done. But we said earlier we want to have an analytic expression. So that's why we make a few more assumptions. You see, you have an exponential minus 1 over RT. That is two nonlinearities. Now we could do just a series expansion. We could linearize this, but then you would give up the exponential dependence. You don't want that. You want to keep the exponential dependence. We know this is very important. So, but there's a 1 over temperature, and at least the 1 over temperature, that's a nonlinearity that we can get rid of by doing an expansion here. So we just take this 1 over t and expand it in 1 over t. So we get this term around tb times plus, and then this is the second order term times t minus tb. So it's just a linearization of the argument of the exponential. And then the second thing we do is to introduce this non-dimensional temperature here. Is the temperature minus TB. So T minus TB now, that's a relatively small quantity because the activation energy is large. So you see if this is order 1, then this here is very large because E is large. This means this becomes relatively small. I mean, if this is an order 1 quantity. So so this is the non-dimensional temperature. You introduce these two things here, and you get this. Okay, so you have temperature times temperature squared, and then that plus temperature squared, and then the whole thing here times exponential of temperature. And this is just a constant. So now we can integrate this. This is the integral we want to evaluate. You can integrate this, and this is what you get. So at least you can now analytically integrate this. Because of this expansion. You see it still doesn't look very nice. It doesn't look so nice, but it's an analytic solution, okay? So now we have an analytic solution, but we also want it to look nice. We want it to be simple so that we can understand what's going on. So here we're making a few more assumptions. First of all, again, we're talking about the limit of high activation energy. First of all, we replace theta I by theta U. Why can we replace theta I by theta U? Because in the theta I appears here in the exponential, and again, you know, so I think this is written here on the next slide. Below theta Ti, or let's say the source term evaluated at Ti is very small anyways, and if I replace it by the source term evaluated at Tu, is basically the same thing. It is very small. Then, so I can replace these. Then, in addition to this, I now I have exponential. I have two terms: the exponential of theta U. Exponential of theta U basically is is very, very small. It's negative, is minus infinity. So exponential of minus infinity here is 0. And so these terms with exponential theta I, they disappear. Okay? So all that's left then is just this here. Okay? So now in the preheat zone, so this was just the right-hand side, basically, of the equation. And the left-hand side also we can do an approximation. Now we can say the preheat zone, we can replace Ti by Tb. So in the reaction zone, we replaced Ti by Tu because we're talking about the exponential of the temperature. In the preheat zone, we have this, the solution to the preheat zone has this thing here, Ti minus Tu. But for large activation energy, Ti is actually very, very close to Tb. For infinite activation energy, they would be almost the same. So that's why we can say, for the purpose of this difference here, we can replace Ti by Tb, and we make only a very small error. Or in the limit of infinitely large activation energy, no error. Okay? So if we do these two things, then you see here, this is what you had in the preheat region, this is what we have in the reaction zone, and now we can equate these and solve them for SL, and then this is what you get, is the square root, which has this exponential function here of Tb, and it has this S function, and S here contains mass fraction of O2, mass fraction of fuel, and this term here. So you see this S term, it depends on equivalence ratio. For very lean mixtures, this here would be 0. The fuel would be 0. For rich mixtures, this would be 0. And for stoichiometric mixtures, both of these would be 0. And that's just this term here remains. Okay? So we can approximate this like this, where we say this is the burning velocity, and then the S term here for very small equivalence ratio, it should just be this. For very large equivalence ratio, it should just depend on the fuel. And for stoichiometric or around stoichiometric, it's just this term that matters. Okay? So this is just this is the final approximation. And now you see, you really get a relation between the burning velocity and the temperature, the transport coefficient, the activation energy, and all of this. And you see how all these things, interact. Okay? So, see what this says here. So this is just a summary again of the assumption. Preheat zone, we neglected the reaction rate. Reaction zone, we neglected the convection term. And we made some approximations. I mean, you can go through this. We just talked about this. But these are all the assumptions we made. What's interesting here in the original derivation, the original derivation was a little different. It was just assuming first order with respect to fuel and oxygen. It was, so this here is first order in fuel and first order in oxygen. The original derivation was done for, and what you see here, it doesn't matter if it's oxygen or fuel, basically it's a T squared. Okay? So the original derivation here said maybe did one that is 0th order, one's first order, one's second order in these quantities. Okay? And then you get different results and you compare them to each other. You see that the present derivation here, it shows that the second order actually, that would be right for stoichiometric conditions. Okay? And first order would be right for either very lean conditions or very rich conditions. Okay, so this is what's mentioned here. Okay, so this is the result, and now we can look at what does this mean in terms of these integral quantities that describe the flame, the flame thickness and the flame time. And the first thing we note here is that if you look at this, what does it say here? There's a square root, and then there are transport coefficients here. We said earlier transport is very important, and we said earlier chemistry is very important. And so you see there's a transport coefficient here, is lambda over Cp, okay? And then all the rest here depends somehow on the chemistry here, the composition here, S, the exponential, and all these things. So we can write SL here as this. The square root of a diffusion coefficient divided by Tc, where now the diffusion coefficient is basically here this lambda over rho Cp, that's the diffusion coefficient, and Tc is all the rest. All the rest has dimensions of a time scale. And so, so that's what it is. So the d here is just this, and the Tc is all the rest. This is the chemical time scale. And what's interesting is you have this Zeldovich number that appears here in this term. The Zeldovich number is the activation energy times Tb minus Tu divided by Tb squared. Or you could say the Zeldovich number really, it compares this non-dimensional group that compares the heat release with the activation energy. Okay, we said earlier that combustion is self-accelerating and non-linear because you have a heat release, and that makes reactions fast. But how strong the effect of a temperature increase is on the reaction rate, that is determined by the activation energy. Again, if activation energy is 0, there's no temperature dependence, right? If it's very, very large, then you have very, very strong influence. So this ratio of activation energy, or this is a non-dimensional activation energy, E over RTB. There's a non-dimensional activation energy. And then Tb minus Tu divided by Tb, that is a non-dimensional heat release, basically, let's say, or temperature increased through combustion. So that is what this number here measures. And the larger the Zeldovich number, the stronger the nonlinearity, the stronger the effect of a temperature change on the reaction rate. And you see this depends on the square. The chemical time scale depends on the square of that. Now, one thing that's interesting is that you could also determine a chemical time scale. I mean, let's say naively, you would say, okay, I have a chemical source term, which is, Y fuel times Y oxygen times this exponential function. And if I divide this by one of them, by one of the mass fractions, then I have a time scale that gives me a time scale. Or not the mass fraction, but one of the concentrations that gives me a time scale. Okay? So this here, for example, this here would be for this is lean conditions. This should be for rich conditions. This would be, a time scale, and but you see, this here is very similar to what we just had. It's very similar to this because the S has all these mass fractions here, and then you get this. Then you get this exponential term, which we have here also, except that this here has the square of the Zeldovich number. Okay? But the Zeldovich number is on the order of 10. So the difference between these two, the difference between the real chemical timescale that we just computed with a full analysis and a naively formed chemical timescale just from, looking at the reaction rate is about a factor of 100. Okay? And so this shows you that just a naive way of defining this timescale is not right. It shows you, and this is very important, it shows you that the flame structure itself determines the chemical timescale. It shows you that in a flame you have interaction of chemistry and transport. In a premixed flame, this coupling between transport and chemistry is so strong that the chemical timescale is not just determined by the chemistry, it's determined by the transport also. Okay, we should always keep this in mind. This is very important for modeling. For modeling, this means in a premixed flame, you cannot just model the chemical source term and you model the transport somewhere else. It means these always have to go together. They always need to be modeled together. This is why, for example, you know, these burning velocities make a lot of sense, because when you take this level set equation I showed you earlier, where all the influence of chemistry is just in the burning velocity, that's exactly what this is. It's modeling the transport and the chemistry together, just put it all in the burning velocity and then just use this jointly modeled term. Now we can also define, so this chemical timescale, we can also define a flame thickness. Flame thickness, LF, here could be defined here as, so now we have the diffusion coefficient is a very important quantity, SL is a very important quantity, and by just dimension analysis, you see the flame thickness should be D divided by SL, or D here for the unity Lewis number is rho divided by lambda by rho Cp and SL. Okay, that's the definition of the flame thickness. Pardon? Yes. So when we talk about these global general things, really we assume the Lewis number is 1. That's why I'm going back and forth between a D and a lambda over rho Cp. Okay, because but the D here, when I say D, that's really the heat diffusion. Why? Because I mean, first of all, you get this coupling function only for Lewis equal 1. We use the coupling function in the derivation of the asymptotic result, and in the asymptotic result, we just solve the temperature equation. So in that temperature equation, this is the diffusion coefficient. Okay, so when I say diffusion, I mean heat conduction.
I saw another approximation with the Schmidt number.
Mm-hmm.
So also the other, besides the thermal diffusivity, the mass diffusivity, the kinematic viscosity will be also 1 compared to the mass diffusivity.
Did I say this here somewhere? I think because you don't solve the momentum equation, that it doesn't appear. This parameter just doesn't appear. I mean, we just talked about it. Somebody asked, why don't you need the momentum equation? The reason is, typically, you have 4 unknowns. In 3D, you have 4 unknowns. U, V, W, pressure. Okay? And you have 4 equations for this. The 4 equations are continuity equation, plus 3 times 3 momentum equations. Okay? 4 equations, 4 unknowns. In 1D, there's only 1 unknown. Okay? And I need just 1 equation. I can take the continuity equation. If I could also say, for that I solved the momentum equation, but the momentum equation involves all the other velocities, involves the pressure, then I need to solve everything together. If I just solve the continuity equation, I get from this U, and I don't need anything else. Okay? One equation is just enough, and I can take the continuity equation. Okay? Okay, so that would be a definition for the flame thickness. Then I can define a flame time. Now we define the chemical time scale, okay, which, you know, chemical time scale. We can also define a flame time. Flame time, that would be the time that the flame takes to advance by 1 flame thickness. Okay? So this is given here, flame thickness divided by SL. This is exactly the time you need to advance the flame by 1 flame thickness. And now if you, I mean, it's obvious, but it's a subtle thing. Which is interesting. is that if I compare this now with the earlier relations, then basically you see that the chemical time scale has to be equal to the flame time. Okay? It's a subtle thing, but sometimes we think the chemical time scale is very, very small. And the flame time is a macroscopic quantity. Is how long does it take for the flame to move from here to here, basically? I mean, by one flame thickness, whatever. But this shows these have to be the same because the flame structure, it influences the flame time. It makes it, the chemical time scale, it makes it slow by just, providing more or less reactants to the place where they're needed. Okay, flame thickness, we just defined the flame thickness, but we can also say, well, how would you define really a flame thickness? No, we didn't define a flame thickness. We just say, from scaling arguments, this is how a flame thickness could be. We could also define it. From an experiment. Let's say you have a temperature measurement in a flame that looks like this, and then here's how you define the flame thickness. You just take the maximum gradient, or maybe the gradient at the ignition temperature, and then you extend it to the burned and the unburned, and then where this line here crosses TB and TU, the distance between these 2 points, that's the flame thickness. Okay, so it's just approximating this flame by this step function or whatever you want to call it. Okay, that's how you would define the flame thickness from an experiment. And we can also, because we have relations here for this dTdx, at the ignition point, we can also evaluate it now from our theory. And then you see here dt by dx, that would be Tb minus Tu divided by Lf. And then, this is the right-hand side. So if you set this T equal to Tb, then you get for Lf, you get the same thing we defined earlier. So what we had defined earlier was not just the scaling argument that roughly scales with a flame thickness. It is something that, using the thermal flame theory, gives you exactly this definition. Okay? That's just something to keep in mind. Okay, any questions about this, about the thermal flame theory? Yes? Yeah, no need, but they're not defined in a way. They just come out of a certain perspective. Okay, perspective number one was we do an analysis and we see at the end of the day you have a transport coefficient part in your final expression, and then something that has the dimension over time scale. That must, and it depends only on the chemistry. That must be the chemical time scale. Okay, there was one perspective, and the other one was to say, how long does it take for a flame to go from here to here? Let's define this as, a flame time. This is a macroscopic thing, and we just found these are the same.
So if the conditions or assumptions are relaxed, then maybe they're different?
Yes, if you say maybe you do multi-step chemistry, maybe things are a little different. But at least under these assumptions, it turns out they are the same. But even if you do multi-step chemistry, is not this Zeldovich number depends. It won't go away. It will just stay there. Okay. So is this break time now? Yes. So let's meet back then at 11:10.